Good evening, everyone. I am Vinod Venugopal, currently serving as Chapter President-elect and one of the Chapter Board of Directors. On behalf of ASHRAE Bahrain Chapter and BOG, I welcome all our chapter members and all other participants to today's webinar, Oversized Air Conditioning System and Overcooled Building in Hot and Humid Climates by Dr. Chandra Shekhar. Dr. Chandra is a fellow of ASHRAE and the International Society of Indoor Air Quality and Climate, ISIAQ. He is working as a professor at the National University of Singapore for the past 3 decades. A special welcome to Professor Chandra Shekhar. Now I am handing over to Mr. Prajesh, our chapter technical transfer committee member, for giving a small presentation about ASHRAE Society and chapter. Over to you, Mr. Raj.
Good evening all. ASHRAE Code of Ethics. Myself is Prajesh. In the ASHRAE Code of Ethics, in this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and we shall avoid all real or perceived conflicts of interest. Next is the contribute or the give back to ASHRAE. The Research Promotion Committee manages and supports both the social level fundraising and chapter level fundraising of the RP campaign. The traditionally supporting just research, the RP campaign was expanded 10 years ago to include support of education and ally, the endowed research through ASHRAE Foundation, YA programs, ASHRAE scholarships, and the general or unrestricted fund. The research, the backbone of ASHRAE, remains the primary fund of the program with over 2 million USD rise for this program annually. For the joining ASHRAE, please contact the below numbers: Mr. Pankaj Amin, the past President MP Chair, Mr. Vinod Venugopal, President-elect and MP Co-Chair, and Mr. Maitam Ali, the Student Activity Chair. The telephone numbers are below. There is a many the ASHRAE Global Training Center online training web series. You can go through the below slide and as well as go through the site. There is a site given below. There is a lot of ASHRAE certification programs. ASHRAE currently offers 7 certification programs: the Building Commissioning Professional Certification, Building Energy Assessment Professional, Building Energy Modeling Professional, Certified HVAC Designer, High Performance Building Design Professional, Healthcare Facility Design Professional, Operations and Performance Management Professional. Our new member, welcome to our ASHRAE Bahrain chapter, Mr. Pantu Bepula, and can go to the next page. There is a presidential message. It's personal growth, global impact, feed the roots. Basically, sponsor for the technical improvement, leadership quality, to exchange the knowledge, sharing theories and experiences. So, this is about the brief about Mr. Chandrasekhar. Mr. Chandrasekhar is currently a tenured professor and program director, MSc Building Performance and Sustainability, and co-director Center for Integrated Building Energy and Sustainability in the topics in the Department of the Built Environment at the National University of Singapore. He is also founding director of Enhanced Air Quality Pte Limited, a NUS spin-off company incorporated in June 2004, arising out of his research in the field of IAQ and energy. He holds BE, Mechanical Engineering from the University of Rajasthan, Malawiya National Institute of Technology, India, and PhD Mechanical Engineering from the University of Adelaide, Australia, in the area of energy efficient cooling and dehumidification systems. He has been a faculty at NUS for the past 3 decades, where he teaches at all the levels and conduct research in the areas of thermal comfort, ventilation and indoor air quality, energy efficient HVAC systems, building energy analysis or management, and integrated building design or operation. Has published around 300 papers in the area in several international journals and conferences. Dr. Shagar is an associate editor of ASHRAE Science and Technology for the Built Environment Journal, regional editor Southeast Asia Indoor and Built Environmental, and editorial board member of Energy and Buildings and Environmental, International Journal of Ventilation and International Journal of Sustainable Energy Environment. Is a co-inventor and hold 3 US and other patents in the area of energy efficient air conditioning system with zonal ventilation control of enhanced IAQ. He is a member of International Science Committee of several IAQ and energy conferences. He was the chair of steering committee for ASHRAE IAQ 2010 conference in Kuala Lumpur in 2010, and continues to be the steering committee of subsequent ASHRAE IAQ conferences: Vancouver 2013, Alexandria, USA 2016, Athens 2021-2022. Mr. Shagar is a fellow ASHRAE and International Society of Indoor Air Quality and Climate. He has been ASHRAE Distinguished Lecturer since 2016, and he has been recognized many awards, including E.K. Campbell Award of Merit and Environmental Health Award. During this COVID-19 pandemic, Dr. Shagar has been an active member of 2 teams, residential and application of ASHRAE Epidemic Task Force. He is also a member of the WHO Environmental Engineering Control Expert Advisory Panel for COVID-19 that published the roadmap to improve and ensure good indoor ventilation in the context of COVID-19 on 1st March 2021. I will hand over the mic to Mr. Chandrasekhar for the presentation.
Thank you so much, Mr. Prajesh. Thanks for those very kind words of introduction. I think I can share my screen now, correct? Yes, okay. Are you able to hear me clearly? Is it fine?
Perfect.
Yes.
And you are able to see my slide? Okay, you are seeing my slide as well, right?
Yes.
Okay. Let me just arrange my screen, and I'm going to go full. All right, so let's get started. So I would like to thank the Bahrain chapter of ASHRAE for inviting me to do this webinar for, I don't know, not just a chapter, I guess, but to anyone who is interested in listening. And that's been the beauty of this pandemic time, I guess. Events like this can be, heard by members of ASHRAE in other chapters and other regions. I've done several in the last 18 months or so on the webinar platform, and usually, people from different parts of the world get connected, and that's really the technology making all these things happen. So let's come to this this evening's presentation of mine, which is titled Oversized Air Conditioning Systems and Overcooled Buildings in Hot and Humid Climates. The time now is about 10 past the hour. I'll just say the hour because it's 9:10 p.m. in Singapore. You're probably 5 hours behind. That will make it, I don't know, is it 4:10 p.m. or 5:10 p.m.? I'm getting mixed up when I try to make the time in different zones in my mind. In any case, it's 10 past the hour. I'll probably do my presentation in about an hour or slightly less than an hour, and then we can take Q&A moving forward from that point in time. This topic is certainly of interest to me, has been for a long time. And I think it's also an interesting topic for several of us who are trying to address the issues related to climate change and how HVAC systems impact and so on and so forth. This particular presentation is AIA accredited, and it's also accredited by GBCI, US GBCI Green Building Council. And It's got a 1 hour general CE hours for this particular event. I will not read all the details here. Some of them are quite straightforward. It just describes what this presentation is about. Let me go straight to the objectives. I have put down 4 objectives here. And the way I would like to look at it is try to understand some of the challenges involved, the psychrometric challenges involved in cooling and dehumidification when it comes to, say, hot and humid climates. Try to perhaps even look at some of the quantification of the energy penalty that might result from overcooling in summer or in the cooling period. I'll also try to address the issues of thermal comfort or other discomfort that might happen if we do not address in a more holistic manner. And I'll discuss the details with you later as we go along. And then finally, some of the engineering solutions, the way we see it, some of them we've applied ourselves in our own buildings, and we see benefits of improved comfort as well as improved energy efficiency. So what's the problem? Where does it impact? Pretty much a good part of the global population. We have more than 2.5 billion people living in the tropical belt, if you like. And then you will see here that the impact in terms of the need for air conditioning is just tremendous. And then we always have to contend with how we're going to manage this ever-rising demand. Even as we speak, we are just we're still part of the COP26 discussions happening in Glasgow, and a lot of the discussion points that I'm sure you must have heard on the news and otherwise, there is a need for us to address the ever-rising energy demand in a more holistic manner and try to address the problem by all means from all the angles that we can think about. So 3 big questions that I would like to pose in my presentation, and I would like to give my talk based on these 3 questions. Why are air-conditioned buildings in hot and humid climates so cold? Because that's the first question we want to ask ourselves. Then comes the natural question, a follow-up to that if you like, which would say, can we raise the indoor set point temperature in these overcooled buildings? Can that be a viable solution? We will look at that if it is possible, and if so, what are the pros and cons? And finally, as I said, what are the engineering solutions to the problem of overcooling in buildings in hot and humid climates? So if we start to look at it from a very fundamental perspective, this is a schematic diagram I use very often, even in my lectures to my graduate students here. It's basically saying that if you have a room that needs to be provided with environmental control of some sort, cooling and dehumidification in our case in the hot and humid climate context, and we use a lot of recirculation, which I'm sure is probably the case in your situation as well. We use up to 90% of the recirculated air. So I just want to highlight the cooling coil over here playing an important role in the air conditioning process. And I think the importance of that is easily seen because the ultimate environmental conditions in the room and in multiple zones of a large central air handling unit that serves a floor or an entire building, even if it's not too high-rise a building, the environmental conditions here is a function of what happens in an air handling unit and certainly a very clear function of the cooling coil. And I will like to discuss some of the nuances involved with cooling coil performance. And the reason I show this diagram is to just highlight that that's one of the focal points of discussion of what I'm going to talk about. So let's come to the first question. Why are air-conditioned buildings in hot and humid climates so cold? And I think I would like to attribute this to the cooling coil performance, which has an important bearing on what the temperature is going to be in the room, what the humidity condition is going to be in the room, and then of course it has an impact on indoor air quality as well. Why I say that? I say that because the total airflow that's going to be supplied into the room, the supply air, is going to involve ventilation. The outside air that we take from the ambient conditions, ASHRAE standard 62.1, and you may have your own standards in Bahrain, for instance. We have our own core requirements in Singapore. At the end of it, no matter where you are, you need to provide the ventilation requirement almost like a mandatory requirement. So if you want to ensure that minimum ventilation is being provided, change in the supply air needs to be ensured with the minimum provision of ventilation air. So therein you notice that there's a challenge in terms of the changing dynamics of the cooling load in the space, because that load keeps changing up and down. You have a design load probably not happening more than maybe, I don't know, 5–10% of the time in the year. Most of the time it's probably about 70–80%. And certainly in the last year and a half, almost 2 years, with the COVID-19 situation, occupancy has been cut down to say 25%, 20% sometimes, and then we do have a challenge. It's the same cooling coil that now requires to function effectively in terms of the temperature and humidity requirements to achieve the correct environmental conditions. Now, why is this a problem now? And could we not do what we have been taught in standard air conditioning textbook? Well, if you think that there is something that we can do, let's revisit that. So the key design criteria for room environmental control or building environmental control is change in the room loads, that's the room sensible heat ratio, and then we have the cooling coil performance, the coil sensible heat factor, if you like. The two must be working in sync, so to speak. If your room requires more latent cooling, your cooling coil must be able to provide that latent cooling. If it can't provide the latent cooling, then we have a problem of humidity control. So the operation of the cooling coil, as you know, is typically by chill water modulating valve. And when you start modulating the chill water flow, you have less and less water going through the coil. Let's think for a moment. The surface temperature of the coil, which is made up of tubes and fins, it needs to be kept cold. If it is cold, it'll dehumidify better. So the colder the surface temperature, better is the dehumidification. Now, when the loads are dropping in the room, when we are starting to modulate the chill water flow, what is happening is we are reducing the chill water flow, and then the surface temperature, in fact, instead of getting colder, it might get slightly warmer, relatively speaking. The reason for that is this entire coil that was selected for design is not too big. And the only thing we can do is we can throttle the chill water flow. Now, I just asked the question just a moment ago to say, can we not do certain things that we have been taught before? Now, what have been taught before, say, from the early air conditioning textbook understanding? Well, this is a psychrometric representation of your room condition, which is 4. Outside condition is 1. We have a mixed air condition here. That's the cooling coil performance. We have an off coil condition, and here is what we call the room sensible heat ratio, right? You want to achieve the room at 4, keep the room at 4, the off coil needs to be at 5. I'm saying off coil here because maybe, you know, off coil supply air, we just ignore the duct heat gain over there. Let's just say the off coil needs to be at 5. Now what happens is, if the coil is too large, oversized, then we still are trying to maintain the temperature at 5, off coil temperature, but because we are throttling the water flow, the coil will not be able to reach 5, but it will be at the same temperature, slightly higher humidity. In other words, it is unable to dehumidify adequately. That's one issue that we might face. To overcome that, we might say, okay, let's overcool. When you overcool, you go to the left of 5, and then we are here in this point, which is fine. Overcooling is what we have been taught before. You can overcool and reheat. Now, when you overcool, there is an extra energy consumption, and then we reheat, which is also an additional energy penalty. Now, most countries, for comfort air conditioning, you can't use reheat. In Singapore, we can't use reheat for comfort air conditioning. Reheat meaning active reheat for sure. Of course, you can incorporate a heat pipe, or you can incorporate waste heat. That's a different discussion altogether. But if you're expecting the cooling coil to give you that kind of temperature and humidity control, we notice that an overcooling process will inevitably lead to the room condition being overcooled. So you have the inevitable scenario of the room being either too cold, and you leave it at that. That's what most buildings used to operate on in the past. By past, I mean 10, 15, 20 years ago. Or you just say, okay, I'm not going to do that, but I'm going to do something like this, maintain the off coil temperature, but keep the room at 4, which means you may not have enough humidity control. So the consequence of something like not enough humidity control in the off coil temperature means the room humidity might go up. So one of the things we often experience people say, and then we also have observed, is that the space humidity level goes up. And that's something that people may not readily accept. Overcooling is also not readily acceptable to people because they would then have to get a jacket to the office environment in a hot and humid climate, which is kind of, it's strange, isn't it? Why would you want to get a jacket in a place which is otherwise hot and sunny and bright, outside condition? So we come to the next question. That I have three questions, I said, right? The second question is, would raising the indoor set point temperature in overcooled buildings be a viable solution? What I mean by that is, can we raise the indoor temperature? It's getting 23, 22 or whatever. I say, okay, I'm going to try and maintain my room at a higher temperature. If you recall, several years ago in Japan, they started this kind of phenomenon called cool biz. They said, okay, why should air-conditioned environments be at 23, 24 degrees Celsius? Then they said to address the energy efficiency part of it and the climate change impact, let's change all the set point temperatures to 27 or 28 degrees. That's what cool biz was all about. And then they said that to do that, you need to adjust a few other parameters. And what are they? First, in the first place, people don't have to come in full business attire to work. So you dress light, raise the temperature to a higher temperature, and will that work? So even in Singapore, probably around roughly the same time, about 10 years ago, there was this plan in a lot of buildings to raise the temperature set point. Typically in the 90s and early part of this millennium, air-conditioned buildings in Singapore would typically see about 23 degrees, between 23 and 24 degrees Celsius. So we said, even in our own campus building, what happens if we change it to 25 degrees? Okay, so that was what we tried. It was almost like our Office of Facilities Management encouraged the building users. We have several buildings on campus. Why don't you operate at a warmer temperature? So during that period of time, I had a master's student of mine who was keen to go and explore this particular phenomenon of raising these space temperatures to see what happens in terms of people's acceptance of the environmental conditions. So he studied about 7 offices in that study, used the ASHRAE 7-point scale for thermal sensation. There were 146 respondents who participated. We measured temperature, humidity, air velocity, and computed, the usual thermal comfort indices like the predicted mean vote and the predicted percentage dissatisfied. And I will share some results of that with you shortly. First of all, the basic finding that we had here was there was quite a big number of people who were not comfortable, who said that they were not comfortable. Now, mind you, these are responses collected when the temperature was raised to 25 degrees or thereabouts, right? Higher. So what happened here? These are the measurements that were taken during that window of time. There was a AM session and a PM session. Notice the temperature and the relative humidity and air velocity. In the morning, the temperatures were 24 to 25.7, almost 26. In the afternoon, it was 25 to 27 even, or even slightly more than 27. So the thing to note about is we raised the temperature set point in the space. We actually found that kind of temperature, the warmer temperature. The humidity was not so bad. It was within the 50%. Of course, when you raise the temperature, the RH drops as well. So that's what we're seeing. The absolute humidity was still probably slightly higher than before. What's important to take note is the air velocity in the occupied zones was less than 0.1 meter per second. That's a point to take note of. It's an important observation that we need to keep in mind as we look at the subsequent set of results that I'm going to share with you. What did the people say? These are what we collected from the responses from those 7 buildings. 142 respondents, as I said. Look at that. The percentage of dissatisfaction as computed from the responses collected was significantly high. Quite a few of them, ASHRAE standard 55, we say is 80% acceptability standard, but here we saw, most of the places from the subjective responses collected, we are seeing in excess of 20%. That means dissatisfaction. So it's not really, the nicest environment that they would have preferred. If you use the measurements of the temperature, RH, air velocity, we find that it is also, relatively speaking, on the high side. You notice here it's significantly higher than what we would otherwise have got. Now, what does all this mean? It just tells us that the lack of air movement, in our view, was one of the main reasons, probably the main reason for thermal discomfort. So I'm just trying to get across an important message here. Ask the question, could raising the set point solve the problem? Probably not. Just the set point temperature increase will not help. It needs to be accompanied with certainly something like an air movement increase, right? So that was a basic observation we got from that particular study. And then we relate that to the ASHRAE 55-2020, which says clearly that you can have warmer temperature, but you need to have elevated air speeds. We also note from some of our other studies, not directly related to raising the set point temperature, we do other kinds of studies where we notice that the tropically acclimatized subjects, I'm sure you can relate to this point as well, we generally prefer a higher air velocities around us in the range of 0.3 to 0.9 meters per second. And this was an observation we made back in almost 8-10 years ago. Just to leave you at that with that particular observation. I'll come back to continuing that discussion in a short while. The ASHRAE comfort zone, the standard 55-2020, the graphic comfort zone method. I'm sure you're familiar with it, where you see the comfort zone for the summer and the winter comfort zones. And the red one is in the comfort zone. It's also, there's a green one. So if I look at the comfort zone, the summer comfort zone, and then I say that I want to be, should I be in the red zone or in the green zone? Both are comfortable. So should I aim to achieve thermal comfort at a lower temperature, air temperature, or should I try to achieve at a slightly warmer temperature? Because this tells us that you can achieve comfort at a warmer temperature as well, the green one. So the preference would be, or rather we should aim to be in the green comfort zone, whereby in a cooling situation, like in a summer comfort requirement, we don't end up being on the colder side. We can be on the warmer side and still be comfortable. That's the point we're trying to make over here. This graph about the effect of elevated airspeed at elevated temperatures. What you see here, I'll talk in the degrees Celsius, the SI units here. Temperature rise between radiant temperature. This is basically the temperature rise between the air temperature being raised up. So if you take a temperature of 23 degrees, 24 degrees as starting point, then if you raise it to 2.2, 1.1 degrees Celsius, 2.2 degrees, 3.3, that's the increase, raising it, the elevated temperature, right? Temperature rise. This is the airspeed that we talk in meters per second. Now, what you see here is the neutral line, meaning the radiant temperature, the mean radiant temperature is equal to the air temperature. So here there is no difference between the radiant temperature and the air temperature. That's the line. If you raise the temperature set point and you get the room temperature to be elevated by 2.2 degrees, you need to have 0.6, 0.78, 0.7 something. So you are increasing the airspeed. One thing to take note of here is when the radiant temperature is less than the air temperature. In other words, the air temperature is greater. TR minus TA is negative. Then you notice that the elevated airspeed is less effective. You see, it's only over a small range that you get the benefit. But on the other hand, if you go TR is greater than TA, that means your radiant temperature is more than the air temperature. If we are in that sort of situation, we notice that we have a much larger range of temperature increase where the elevated airspeed is beneficial. So the point to get across here is increased temperature, elevated temperature accompanied by elevated airspeed is a useful strategy. Now we look at some of the engineering solutions that we can consider to address this overcooling problem and see how we can minimize the adverse impact of the overcooled environment. What I'm going to discuss with you are three different strategies, if you like. An oversized cooling coil, which can dynamically change its operating characteristics. Well, the dynamic change is not just in the environmental conditions of the coil performance, but also in the physical geometry of the coil. That's what I'm talking about in the first one. The second one is cooling coil optimization, depending on what kind of delta T you can work with between the room condition and the off coil and so on and so forth. The third one, finally, I will discuss with you the dedicated outdoor air system with ceiling fans. So three different strategies that would be what we'll be going through for the next half an hour or so. So the oversized coil with dynamic change of effective surface temperature in operation. Important point to take note here is the dehumidifying performance is critical, and we can get an increased or better dehumidifying performance when you follow this particular concept that you see on the slide, a low face velocity. This is a low velocity on the air side, accompanied by a high coolant velocity, which is the chill water velocity going to the tubes of the coil. This combination of low face velocity and high coolant velocity is ideal to keep the interface temperature of the cooling coil surfaces as cold as practically possible. I say that because nothing is infinite in terms of the controllability. Within the constraints, within the thermodynamic constraints that we can expect to have in any psychrometric situation, this combination is going to be perfect. As a quick pragmatic understanding of what happens, all of us know that a VAV system in part load condition will actually give you better dehumidifying performance compared to a constant air volume system. A CAV, high face velocity. VAV, low face velocity. You straight away get the benefit of the lower face velocity, helping us to maintain the interface temperature. I will discuss with you some of the points here. The points here, I already mentioned the interface temperature, and I mentioned about the low face and the velocity and the high coolant velocity. What happens here, I'm going to take you through the dynamic operation of this cooling coil. We would have, say, the design condition, peak design, 6-row cooling coil. Looks very similar to a conventional cooling coil, but the way in which it's going to be physically installed is slightly different. What we do here is the supply manifold is here, chill water supply to row 6, 3 rows, you feed through those 3 rows and collect the water at after the 3rd row. From here, the chill water goes to row 3 through another set of manifold, and we have a 3-port 2-way valve, so the water can go straight that way or it can come this way. In this configuration, it's coming to row 3 to 1. So basically, we supply to 6 and pull out of 1. In this configuration for peak design condition, no different from what a conventional design might look like. The only difference here is after row 4, we collect the water and feed it into row 3. There's a reason for doing that. How does the whole operation work? We have a counterflow arrangement, as you can see here, airflow this way, the coldest water meets the coldest air. That's the counterflow arrangement, so that the log mean enthalpy difference is the same throughout the entire cooling coil region, so to speak. As the loads drop, we have the modulation of the chill water valve, and that's the modulating valve, and that's the standard strategy. We modulate it. We keep closing the valve until such time we notice or realize that the loads have dropped so much that it is almost 50% or 60% of the load, the total load, for instance. At that time, we're going to do something like this, where we say these 3 rows are going to be inactivated. We only use row 4, 5, and 6. Notice what has happened. We close this valve and the water goes straight after the 4th row into the modulating valve. So basically, we have converted effectively in dynamic operation a 6-row coil to a 3-row coil. And that is helpful because the large coil, the oversized coil, can now be managed through the chill water flow, the chill water circuits, in such a way that we can actually achieve a higher water velocity if that's going to help us, and we know it's going to help us. We are not going to increase the water flow any more than what is the design flow rate. That's not what I'm saying. I'm saying that the modulation of the water flow is going to be better controlled, so that we are able to move that design flow rate through a smaller number of rows, smaller effective surface area. And that means the high coolant velocity is achieved. The combination of low phase velocity and high coolant velocity will help us give that kind of cold interface temperature. We call this the adaptable cooling coil that can adapt itself in the dynamic operation over a range of operating conditions. So the findings here is that the challenge with oversized cooling coil because we just keep modulating and there isn't enough water flow to maintain that cold interface temperature. And then if we can change the surface area from a 6-row to a 3-row coil, it helps us manage that coolant to basically allow us to flow rate and thereby the coolant velocity to get that cold interface temperature. Level of optimization on the cooling coil performance, where we're talking about the space temperature difference, the delta T between the room and the off coil or supply air temperature. And then we can look at the cooling coil performance itself, the fan performance itself, and how all of these are related to the energy and indoor air quality issues. So we are basically talking about these three aspects: the cooling coil, the fan, and the space delta T. And there is a publication on this, and we did this several years ago. And the comparison here is, if we want to explore, say, 4 different space delta T, and this is probably easier to understand. The room is being maintained at, say, 23 degrees, as we see here. Then we have 4 different space delta T. The base case is what I'm calling as a space delta T of 8 degrees Celsius. That's over here. And A, B, and C, D, these are the points on the mixed mixing line, so to speak, where we determine the entering condition of the cooling coil. Nothing fancy about it. When you reduce the total airflow, supply airflow, maintain your ventilation airflow, obviously you're getting closer and closer to the outside air condition. So just evaluating different scenarios of this nature, chill water supply temperatures maintained at 6.7 degrees Celsius. What it shows us is, in terms of the cooling coil performance, if you were to achieve the same level of room conditions, there is, if the 8 degrees space delta T, there is, as the base case, relative to that, when we lower the space delta T, you notice that there is an additional energy power requirement. And this comes about simply because we are forced to overcool and reheat. That's primarily the main reason. The cooling energy, as you can see here, has increased here, as you can see here. Cooling energy and electrical power, that's a fan. When you reduce the delta T, more air needs to move, the fan power increases, and thereby the cooling capacity, here's the fan power, it increases, the cooling capacity also increases. So we find that there is going to be an additional energy consumption when you reduce the space delta T and try to operate the condition, environmental condition, the zone in that manner. Another important point that we may want to take note of here is, if we have our off coil condition or supply temperature closer to the saturation line, it's probably a much easier target to achieve than if we were to go away from the saturation line. Especially so from the perspective of latent cooling demand, right? We know that if you hit the saturation line from a cooling coil, performance point of view, that's probably the best condition you're ever going to get out of that cooling coil. If not, the further away from the saturation line, you get some level of dehumidification, no doubt, but not the most optimized one. Then we are also looking at what happens when this is just a graphical plot of the same energy data from the previous table. We are also looking at what happens if you increase the ventilation rate. Here is the base case, 18% outside airflow. Then we are 22% and 26%. Obviously, there's an energy increase. This is just a documentation of the percentage increase, 10% and 17.5% additional capacity. So for this part of the discussion here, the key findings here is your total power requirements, which involves overcooling, reheating, and increased fan power, increases significantly as the space delta T is changed from 8 to 5 degrees C. So we would not want to reduce the space delta T in the context of designing an overall system for any given application. There are a whole bunch of other findings that we are relating to here. If we increase the supply airflow by reducing the delta T, space delta T, it's going to have an implication on the duct design, the duct sizing and the noise levels and all that sort of thing. So there's optimization. What's the space delta T? How much air to move? How do we ensure minimum ventilation? All of that comes into picture when we are talking about trying to optimize the entire room and the AHU as a system level optimization. I want to come to this third strategy. This is actually zero energy building, a first purpose built zero energy building in Singapore. Net zero energy building. It's our own school building. I don't have a office space here, but we do have one of our research center, which is probably right there. That's the research center office that belongs to our group. And this is a very new building that was launched on 30th of January 2019. And it is a net zero. You can see the solar panel that kind of envelops the entire roof of the building. And we are extremely delighted to have this building. For the last 2 years, we've been managing and collecting the data. Admitted, this is during the COVID time with reduced occupancy, but in 2019, we did have data, and I'm going to share with you some data that we collected during the time. First, there is a fundamental difference in the air conditioning design concept. What we do here, we call it the hybrid air conditioning. Conventional systems, conventional air handling unit maintains at 23 or 24 degrees Celsius. We know that, what that is. Thermal comfort and IQ, probably we can control it to everybody's satisfaction perhaps, but the energy is going to be high, no doubt about it, right? If in the conventional system, my second question, can you raise that set point temperature in the room? Yes, when you do that, you save energy, but thermal comfort, IAQ, probably not well managed. So we introduced this DOAS air handling unit. Remember, in both of this, there's recirculation. In the DOAS, there is no recirculation at all. So the hybrid air conditioning is 100% outside air. We supply the air to the room to maintain the room at 27 degrees Celsius. 27 degrees Celsius. Now, same as this, right? 27 degrees. But the difference is we also provide fans, ceiling fans, in a regular grid arranged ceiling fan concept. And then we say, okay, increased air movement. Remember the ASHRAE 55-2020 and our basic understanding of elevated temperature with elevated airspeed can work. That's what we do as a concept. It's called hybrid air conditioning in the way we have been discussing and coming up with the design concept for our building here. It's 27 degrees Celsius accompanied with ceiling fan generated air movement. We did a mock-up chamber study because this building was launched in 2019 January. Now this time frame that you're seeing here is almost a year ago. Year prior to that, when we wanted to test it, of course we can do simulations. I mean, simulations gives us an idea, but then nothing like getting the actual feel for it. So here I had a PhD student who did this work as part of his PhD thesis, and then he looked at 24 degrees, 27 degrees, M0, this is a fan speed, the ceiling fan speed, M0 is 0, M3 is here 0.94 meters per second, and M5 is 1.6 meters per second. 0, 1, 1.6 meters per second, 3 different air speeds. What is finding here, the air movement preference, when it is at 27 degrees with almost 1 meter per second airspeed, hardly anyone is asking for any change. Look at that, no change. They don't want any change. They accept it, they like it. So that's what happens here. Of course, when you actually increase it to higher airspeed, then even at 27 degrees, Higher than 1 meter per second, not everybody wants it because they say, give me less. So basically, we conclude that 27 degrees Celsius, about 1 meter per second airspeed, people will accept it. This was our mock-up chamber study. We had about 32 what we call respondents or subjects participating in the study. There's a systematic experimental design. I won't go into all those details. I don't have the time for that. But then that's exactly what leads to this kind of an analysis. Look at the thermal comfort. Again, we notice that 27 degrees and 1 meter per second, that's here, comfortable. The dark blue bar is comfortable, and this is hardly anyone is uncomfortable, right? The interesting part, and I would like to really stress upon this, the IAQ acceptability, the indoor air quality acceptability. Whether it's 24 degrees or 27 degrees, almost 90 to 95%, they like it. Why? Because we are supplying 100% outside air all the time, whether it is for 24 degrees or 27 degrees. Now, that's the big difference. Remember the experiment, that the study I shared with you as part of a second question that I was discussing with you. That means we in buildings and anywhere we raise the temperature to 25 degrees with recirculation. People did not like it that much, and no air movement. Two things were missing, right? There was recirculation and there was no air movement. Here, when we don't have recirculation, provide the right amount of ventilation, maybe even more than the usual amount, people like it. IAQ acceptability is good. This was in the mock-up chamber study. He continued this study as a field validation in the SDE for net zero energy building, which is what you see on this picture here on the slide. This was after it was constructed, 2019, it was January, it was launched. These studies were done sometime in the first half of 2019. And he did the studies on this floor, studio space, for 4 different regions of this large studio space, very large space here. And he also compared that with a conventional computer lab that used a conventional fan coil unit. So this is 24 degrees and this is all 27 degrees. And here are some details about the airflow numbers and how many fans there were, the number of people who were involved in the study. And here is a publication that was published earlier this year. It came out in the print form in Building and Environment Journal. Now, measurements. The measurements here clearly show you that the temperatures that were actually being achieved there were, you can see at 27, 26.7. So, we designed it, we're operating it that way. The humidity was about 60% thereabouts, not an issue, right? The globe temperature, which is an indication towards our mean radiant temperature, not significantly high compared to the air temperature. So you can take it that we didn't have too much of a radiant heat impact in that studio space. The computer lab, which works on the conventional system, 24 degrees. That's really what we're comparing. 24 degrees conventional, 27 degrees DOAS with the ceiling fan, enhanced air movement, right? What did we find here? Here again, some basic comparison. Studio, there's 1 to 3, and then studio year 4, computer lab. Look at this number. These are numbers about what exactly was the maximum and minimum or average outdoor airflow rate. But the average outdoor airflow rate supplied in terms of CMH per meter square is typically about the same, whether it was the computer lab or in the studio space. However, when we track with the data collected for mean daily energy consumption, this is a computer lab normalizing for all other parameters involved in such a comparison. We notice that we get anywhere between 26 and 30% energy savings. Not surprising, when you maintain the space at 27 degrees, you actually are saving, reducing the cooling load to begin with, and you are saving on the energy consumption. And the fact that we are not pumping a lot of air at a very low temperature also helps us to save the energy here. And of course, the ceiling fan energy consumption is again normalized. We have added that as an energy penalty in these two scenarios. Despite that, you notice that we find about 26 to 30% energy savings. So the point again I would like to convey across through this concept is, in hot and humid climate, maintaining the space at 27 degrees Celsius, accompanying that with enhanced air movement, certainly seems to be a winning formula. People like it. This was accompanied with subjective response studies too. I don't have the time to talk about that in much detail, but it was very similar to what we found in the mock-up chamber studies. These subjects who were occupying these premises here, the students who are occupying these premises, they actually, through their questionnaire survey responses, voted that they liked the environment and they were acceptable. I would like to add one point that we need to bear in mind. The fact that the temperature of the air is 27 degrees, when someone walks into such an environment, there is a transient effect. By transient effect, I mean if you're walking from an outside environment, you're already sweating, and you enter into a space like this, for the first probably about 10-12 minutes, you might desire for an increased level of evaporative cooling. In other words, the fan speed to be even higher than the 1 meter per second I mentioned, or the air temperature to be slightly lower. So operationally, ORCF will need to take into account the effect of the transient situation when somebody walks from an outside environment to an environment like this. But in steady state, if in office environment, they're going to occupy this for 3 hours before going for lunch, or 3 hours after lunchtime, or 4 hours, 27 degrees with ceiling fan generated, 1 meter per second works. That's our finding from this particular study. So in conclusions, let me try to go back to those 3 questions that I set as, my basis, or, the kind of framework. Why are air-conditioned buildings in hot and humid climates so cold? And I think I made the case that it is happening that way because the coil is oversized, the air handling unit is oversized, and an oversized coil will provide less dehumidification unless we employ overcooling. And when you employ overcooling, because we can't normally use active reheat, the space temperature is inevitably left overcooled, and that's the perception that we get. It's so cold. Why should building be so cold? And that's why it's so cold. The second question is, just raising the temperature, set point temperature alone, does it solve the problem? And I think I shared with you that study where we said that just the temperature increase doesn't help, because you create that feeling of stuffiness around the person. The thermal comfort is a function of 4 physical parameters: air temperature, relative humidity, mean radiant temperature, and air movement. Now, we have always been talking about achieving comfort, thermal comfort, by just playing with the air temperature. We are now saying that air temperature alone, if you just play with air temperature alone, you need to keep getting colder and colder. That's the only way you can take care of it. But when you raise it on the warmer side, that increased temperature must be accompanied with increased air movement. Remember, temperature and air movement is part of thermal comfort as an index or an overall response a person experiences. The engineering solutions that we can explore, one, I just straight away said that if you increase the temperature, increase the airspeed as well. When you increase the temperature and thereby the airspeed, it is always a much better idea to not have recirculation, or even if you want to have recirculation, minimize the amount of recirculation. Let me explain to you why. I mentioned to you that example, that study we did several years ago where people said air movement is low, and then they also felt stuffy and didn't like it. So many people voted not comfortable. The reason for that is also air quality related. Here is what happens. All the surfaces in the building, your table furnishings, carpets, ceiling acoustic tiles, building, the partition boards, any other fabric you may have, all of them will emit gaseous pollutants, they outgas. These outgas emissions appear in the air as volatile organic compounds. Sometimes may have some stronger components of formaldehyde, which is not very good from an air quality perspective. basically they emit. When the surface temperatures are cold, the level of emission is kind of suppressed. You don't have that level of emission. But when the surface temperature is raised, which is what happens if your room temperature is increased, the surface emissions increase. So when at elevated temperature, 27 degrees, there is more of the room emissions from all the partitions, the furnishing, building material. Now, if you use recirculation, and if you don't have adequate filtration for gaseous components, not particulate filter, not particulate matter filter, not to remove the particles alone, you need to have VOC removal, gas phase filtration. If you don't have that, you would not have addressed the problem in terms of the air quality, the emission related air quality problem. You overcome that if you're supplying 100% outside air. And that's why we noticed that in our SDE4, the net zero energy building that I shared with you, supplying 100% outside air made people feel that the air was always fresh. It felt fresh because it does go through an air handling unit where we do have a MERV protein in place. That's a requirement from our local Singapore place. That's a requirement standard or indoor air quality. So I think if we are able to ensure that the air quality, the supply air quality is good, with that elevated temperature, we have a lot of things that we can do that accomplishes both thermal comfort and air quality, and thereby we achieve the human requirements for comfort and air quality acceptability, plus the fact that it's going to lead us to energy saving because we are not cooling as much as we would do in a conventional system. Finally, I want to leave this point across to you to think in terms of separating the cooling from the ventilation. In hot and humid climate, it's probably true in your context as well. Ventilation air is for air quality, which also gives some cooling, but the secondary cooling, which is to take care of your sensible cooling load and all that sort of stuff, we can do it by other means. Ceiling fans is one of them, evaporative cooling of some sort. You can have chill ceiling, chill beams, or any other means. Separate the ventilation from cooling. When you have a ventilation airstream that is to be supplied as a separate duct, or the DOAs that I shared with you in that example of the net zero energy building, you can also achieve better level of ventilation control. Like a demand control ventilation can be better managed in that kind of a context. With that, I will end my presentation. I think that's my last slide, and I'm happy to take questions. I'll pass the screen back to, I don't know who's taking over from me, Amo or Prajesh?
Yes.
I'll pass the floor back to you. Thank you.
Yeah. Thank you, Mr. Chandra, for your very informative presentation. There are quite a few questions that we have received now, so I'll try to take a few of them. The first question is: should we always use chill water systems? Can we not use DX plus DOAS using DPT / dry bulb outdoor weather conditions to address latent load?
Yes, you can. I mean, the last point that I just mentioned, if you separate the ventilation from cooling, the actual cooling process can be achieved by, it can be through DX systems or central chill water system, building level. It can be a district cooling plant. So many different ways one can explore that. I discuss what I did with chill water system because that's the most common design concept in Singapore in air-conditioned buildings, in large commercial buildings.
Oh, all right. The second question is: what is the controlling factor to circulate water in 3 coils or 3 rows rather instead of 6 rows?
Well, as I was explaining earlier, we start off with 6 rows of coil. That's the correct size, let's say, for 100% design load. As the loads drop for the coil, you're modulating the chill water flow. You close the modulating valve. When you find that you are close the valve to almost like 10% or 20% position, you realize that the load has dropped significantly. At that point, you would say, I actually want to reduce my coil size. It will be better if I can change the coil to a smaller coil. And that's what we are trying to do. When you are in that situation, which can be determined by a measure of your off-coil condition and the amount of airflow going to the coil and the position of the modulating valve, you will then change it into a smaller coil by making only 3 rows active. So it adapts itself depending on the cooling load requirement in the building.
Okay. The next question is from Mr. Mohammed. His question is, why can we not elevate the air movement by just increasing the AHU fan speed instead of installing ceiling fans into our system?
Well, okay, I understand the question. Think about increasing the central, AHU-based fan airspeed. I mean, you only want to move as much air as you really need. Why would you want to move more air through all that network of ducts? There's an implication on the fan energy consumption, which is something we want to avoid. These ceiling fans, they are very low energy consuming entities, and it's used on demand at a very local level. I mean, not everybody might really want to use the fan all the time. Not everybody want to use the fan at 1 meter per second. Some may want it at 0.5 meters per second. So there is that level of individual control we can provide in the occupied space. So it again goes back to, if you look at it as a overall optimization strategy I mentioned, there's space delta T, there's a fan performance, right? Fan performance was one of them, right? We would not want to move any more air than we absolutely need to move. So if we increase the fan speed to increase the air speed in the space, then I think we are not doing what we really need at the space level without having an implication on the fan energy. That's the main reason I would argue.
The next question is from Mr. Adil. This question is, what is the air velocity generated with ceiling fans when adopting hybrid mode?
Right. So as I was talking about in the mock-up chamber, we were, of course, 0 is when the fan is off. We were trying 1 meter per second and 1.6 meters per second. So our observation from our mock-up chamber study was 27 degrees Celsius indoor space temperature with 1 meter per second airspeed, just perfect for the occupants. And we also found a similar observation, similar finding in the field validation in that zero energy building I was talking about. So we're talking about an airspeed somewhere between 0.8 to 1 meter per second. This speed might have to be increased when somebody walks into the building for the transient effect for the first 10 minutes or so. It may even go up to 1.5, 1.6 meters per second.
There is a question from Mr. NP Singh. He is saying the velocity higher than 0.25 to 0.5 meter per second creates problems in office areas or residential areas, which may result in movement of air curtains and papers may fly. So what?
That is absolutely not seen. Papers don't, I mean, I'm sitting here, paper is not flying. I got the fan running at, if I measure, it's probably more than 1 meter per second. You need much higher, probably 1.6, 1.8 meter per second. But 1 meter per second is a gentle breeze, gentle air movement. All those issues are just not what we experience. And I've felt it in my office building, in the zero energy building. We don't see a draft, if that's what you're looking at. I will agree with you if that kind of airspeed is at 23 or 24 degrees. Oh yeah, definitely. I will never do that. But if you have increased the temperature to 27 degrees, 1 meter per second is not a problem at all. It works.
Okay. The next question is from Mr. Srinivasan. His question is, what is the increase in capital cost by opting for DOAS and the return on investment?
Right. I haven't done an economic analysis, but we know for a fact your AHU is reduced in size, your cooling energy requirement is reduced in capacity, your ductwork is reduced. I mean, everything is reduced. So it can only be lower cost, capital cost. Yes, the ceiling fans is an added capital cost, but in the context of air conditioning components, the ceiling fan cost is, I mean, we are not talking on same orders of magnitude in terms of the amount. So overall, to deploy a DOA ceiling fan system is going, I mean, I don't even see a payback analysis to be done. It's just going to be cheaper anyway.
Okay. The next
Think about
question
it, we don't
is,
have a return duct, we don't have a large size duct. All of that will help in reducing the cost. Yeah.
sorry, yeah. The next question is in DOAS, what will be the air living temperature from AHU to achieve 27 degrees Celsius in the space? The off-coil temperature.
Right. Good question. Yeah. So we designed our system, if I remember correctly, for about 16 degrees or 17 degrees. So it's somewhere between 16 and 18 degrees Celsius. That's the off-coil temperature, which is also roughly what is delivered in the space. So your supply air temperature is about 18 degrees Celsius.
Okay.
It's a little bit like your underfloor temperature and underfloor UFAT system, underfloor air distribution system temperature.
Okay. The next question is from Mr. Mohammed Irfan. His question is, it was mentioned that in DOAS to be used when we use elevated air movement with temperature increase. Is it mandatory to use only with DOAS, or for general AHUs and with outside air will also? I mean, that's the recommended practice to do it with normal air conditioning with recirculating type of AHUs.
The standard 55-20-20 is only about air movement and temperature. It is not about what kind of air we are talking about. But I am sharing that information with you based on our own studies, one with recirculation, another one without recirculation. When you have recirculation involved in a conventional AHU design, and if you increase the temperature to 27 degrees Celsius, I would pay close attention to how much ventilation is being provided. If the minimum ventilation is reduced, then we will have issues of emissions, as I mentioned, and that may not be well accepted by the occupants. And that is something that will need to be evaluated on a I suppose a case-by-case basis as well. But yes, the point is, if you're asking the question, can the airspeed be accompanied only in a DOAS? That's not true. You can use the increased airspeed with warmer temperature being created by conventional AHU design as well. Not an issue. That's not a problem.
Okay, there is one more question, but I'm not too sure whether it is related. How can we increase the efficiency of chill water system?
How can we? So many ways, right? I have another talk that I touch on this particular point. I mean, your efficiency of a chill water system, there is the chiller energy performance we can talk about. At what temperature the chiller needs to supply the water to the end points, the end use points. 6.5 degrees Celsius, 8 degrees Celsius, 9 degrees, 10 degrees. So we currently have a research project where we are exploring the use of chill water at a warmer temperature, and then see if our cooling coil performance can be adequately addressed as well. So that's one impact. The other impact will be how much of chill water flow you move between the chiller and your end use points. So that's where you will talk about using VSD pump to control the amount of chill water flow. Again, the chill water flow will be a function of how you are sizing your coil and how you are designing the coil control. What is your maximum chill water flow? You want to reduce the flow as your base design condition. Then it will say, you see, it's a function, the energy consumption always a function of flow rate times delta T. So if your delta T, by delta T, I mean the chill water supply and the return, that's one delta T you're talking about. And also at the chiller level, if it needs to produce the chill water at a warmer temperature, instead of 6.5, 9 degrees Celsius, you save energy. So it's a multi-optimization problem here, not just one, I would imagine. And it may also depend on how the building loads are. Are your loads more or less stable, or do they fluctuate dynamically on a regular basis? All those things come into picture. I hope I've answered that question in a very generic sense.
Yeah. We have quite a few more questions, but I think because of paucity of time, we'll have to end it here, the question and answer session. But if there are other questions, probably we can email it to you, and if you can reply to those, we can then share it.
I suppose you can do that. I'll try and answer to the best of my knowledge there. We can certainly do that. So once again, I'd like to thank the Bahrain chapter, the Board of Governors who decided to host this session and to invite me to make this presentation. It's been a pleasure. I really like the interactive session. I only wish that we could see each other in person. That would have been even more engaging. What I've been enjoying for the last, since 2006 when I first started my DL journey in ASHRAE. It's been a good 15 years on this DL circuit, but for the last 2 years, it's been more of the webinar style that we're doing now. I enjoy every bit of the interaction, and thank you so much for making this event possible, and really appreciate all that has been arranged so far and the questions that have been coming in the discussion session. Do you want me to unshare this?
Sorry. Yeah, I would like to hand it over to Mr. Adil for the vote of thanks, please.
Thank you, Amol. Yes, Dr. Chandra, you were saying something about this slide.
No, you already done that. I thought I was still sharing my screen. I just asked whether I should unshare from my side.
Okay, thank you. Good evening, everyone. I think you all enjoyed today's lecture, which was really stunning on the oversized air conditioning system and overcooled buildings in the hot and humid climate. I'm sure that every one of us must have gained a good, valuable knowledge. Many good heads up were shared by Dr. Chandra today, and a big thank for him. This wonderful event, what we had today, became possible due to the untiring efforts of our CTTC team, and I can say with certainty that everyone would have enjoyed it. So well-deserved thanks to the CTTC committee of ASHRAE Bahrain. Also, I would like to take this opportunity to thank our sponsors, Daikin Middle East and Al Mahrous for their valuable contribution in making this event possible and successful. We have other series of events lined up for this year, and we wish you all to see again. Regarding this presentation of today, this presentation, as Dr. Chandra mentioned earlier, has been pre-approved for the continuing education credits, and on your screens you can see the number of GBCI approval and AIA approval. So the next program what we have is on 4th of December. This will be done by our RAL regional lecturer, Mr. Ashish Rakheja. And it will be at 5 p.m. Bahrain time. The topic is VRF versus central plants, which is nowadays a very relevant topic and a dilemma for the owners, which one to choose. So till then, thank you very much. And last but not the least, thanks to all of you. Thanks for joining in great numbers, making this webinar successful. And we have a feedback after this, so we can improve in the upcoming events. With this, we would like to conclude this webinar. ASHRAE Bahrain team says big thanks to all of you. Enjoy your evening. Thank you.
Thank you so much.
Thank you.
Thank you, Dr. Chandra.
Thank you. My pleasure.
Thank you.